Hi guys, this is Mrs. Gastler, and in this video we're going to talk about SHMs and SHOs, which is simple harmonic motion and simple harmonic oscillators, which is fun. Alright, so I've got some sort of pre-filled out notes that we're going to go through and fill out as we go. So to begin with, simple harmonic motion. Simple harmonic motion is any motion of a vibrating or some kind of repeating pattern of vibrating object or system of objects that has a restoring force that is proportional. It's opposite and proportional. I'm going to run out of room. Proportional, right here, to the displacement, which we'll talk about again on the next page. We're just going through some definitions to begin with, which is a good place to start. So simple harmonic motion, motion of vibrating object or vibration of object or system with restoring force opposite or proportional to the displacement, okay? So there's some key factors here. It has to have a restoring force that is opposite and proportional to the displacement, okay? If that isn't what's actually happening, then what you're looking at isn't really simple harmonic motion. It might look like simple harmonic motion, but if that's not why it's happening, then it's not actually simple harmonic motion. There's lots of things that look like simple harmonic motion. It might be a repeated pattern, but if it's not a restoring force that's opposite and proportional to displacement, then it's not simple harmonic motion. So that's the qualifier right there, okay? So in simple harmonic motion, when you have a simple harmonic oscillator, that's the object. The object that is oscillating in the simple harmonic motion. Simple harmonic motion. Now, nobody likes to write that out, so abbreviating it SHM is totally okay, and SHO for the simple harmonic oscillator so that you never have to write those out again. It's totally fine, okay? Simple harmonic motion and simple harmonic oscillator can totally be abbreviated in that manner, okay? So let's think of some examples. The example that we used in class is so far a pendulum. I'm going to put a little star by that because we'll talk about later in lesson 2 about some special circumstances that pendulums are actually only simple harmonic oscillators in certain circumstances. That if certain things if something is the case, a pendulum is actually not a simple harmonic oscillator, and we'll talk about why that is then. And then another case that we used in class an example that I showed you in class the other day was a mass on a spring. Okay, and you may be able to come up with some other simple harmonic oscillators, and there's lots of things that are out there that are kind of like simple harmonic oscillators, and they may be simple harmonic oscillators, and they may be pretty close, but maybe not quite. And then there are plenty of things that look like simple harmonic oscillators that aren't, okay? One that isn't, and I'll go ahead and write it here, is a ball bouncing. And I'll let you tell me why it's not, okay? A ball bouncing is not a simple harmonic oscillator. It is a regular repeated motion, but it is not a simple harmonic oscillator, okay? You can tell me why, okay? So when we talk about simple harmonic motion, there are some words that we use to describe it. These are some descriptors, some things that are useful to talk about when we talk about the simple harmonic motion, but they're not necessarily things that we measure, although we kind of can. There's an equilibrium. This is a particular position. This is a location. It is the position that the simple harmonic oscillator would be at if it wasn't if it wasn't in the process of doing the simple harmonic motion, okay? If it didn't have, if there were no initial disturbances, initial initial disturbances. So in order for simple harmonic motion to happen, the simple harmonic oscillator has to get moving in the first place. So it has to get started somehow. Initial disturbance, something has to get it going. Disturbance, there we go. Or some outside force, okay? Outside force, there we go. You know, sometimes you make mistakes. You just cross them out and you keep going. Or you can erase. You can erase, that's fine too. I don't want to. The outside force gets it going. So if there was no outside force, where would that simple harmonic oscillator be? That's the equilibrium position. So that's like a middle ground, a rest position, if it were at rest. But once you get to the simple harmonic oscillator going, it just goes back and forth, okay, over and over again, and it keeps oscillating. So that oscillating motion is back and forth. Side to side, to and fro, up and down, whatever it's doing, it's going to keep doing it for an extended period of time. We'll talk a little bit about what happens or under what circumstances that would not keep happening. And that back and forth motion is called a cycle. Okay, so one complete to and fro motion, they call it a to and fro motion. Okay. And depending on where in the cycle you start, you might have to repeat part of it, or it looks like you would repeat part of it, but it really depends. So if you have an object that's going back and forth like this, okay, like that, so you might have to start, if you started here, you would go all the way over this way and all the way back. But if you started here, you'd have to go all the way this way, all the way that way, and all the way back. And so it might look like you are repeating part of it, but you're actually not. You're doubling back what you are, but you aren't. You're going this way in one circumstance, and you're going the other way in the other. So you're not actually repeating any of it until you start going back that other way again, okay? So you kind of have to be really careful about where you start counting from or measuring from to make sure that you're getting a complete cycle in your to and fro motion. It's easiest to measure from an end like this, okay? The next set of words we've got here are things that we measure, okay? There's lots of things that we can measure about our simple harmonic oscillators and simple harmonic motion. And the first thing we can measure is displacement. We use the letter X, depending on, so sometimes we're measuring a pendulum and sometimes we're measuring a mass on a spring. And the mass on the spring goes in a straight line, so X or Y sometimes, depending on whether or not, if it's vertical or horizontal, you might want to use one or the other, okay? And so if it's a pendulum, though, you might rather use the angle instead. So I'll write it like that. Okay. And that is where it is, where the SHO is. Okay, at a given time. Okay, so and this is relative to that equilibrium usually. I mean, you could put equilibrium wherever you want to. Remember how you can pick where 0 is? A lot of times we usually pick 0. We usually pick this equilibrium place as 0 because it makes things easier. But you could pick equilibrium to be wherever you wanted to. You could pick it to be 10 or 25 or, it doesn't matter. It's just a number. And so we measure displacement relative to that equilibrium. Okay, so how far are you from equilibrium is usually what that displacement is measured to. Okay. And with the X and Y, we usually measure it in meters or centimeters. Sometimes we're talking about small motion, so it's easier to measure it that way. And then the angle would be measured in degrees. Okay. The amplitude would be your maximum displacement that the show reaches. And again, that would be a maximum X or your maximum Y or your maximum angle, okay, that your pendulum or your mass on the spring reaches. We could talk about other things that are exhibiting simple harmonic motion, but those are the ones that we would usually stick with. Okay. The next thing that we could measure would be the period. I've also got frequency down there. That paper is getting in my way. So period is a capital T, which can be a little annoying when you're dealing with a pendulum because the tension in the string is also a capital T, but you can always use capital F for tension on the pendulum, just to make things a little bit easier. Okay, for tension. There you go. That way your letters don't get mixed up. That might make things just a little bit easier. So the period T is the time for one cycle. Okay, the time for one cycle. We usually measure that in seconds. Okay. Although you could measure it in something longer than a second, but usually seconds is all we need. Frequency is usually a curvy F, kind of like that. And it is the number of cycles. If you didn't know, that's the symbol for number. I know it's hashtag these days, but it's also the symbol for number. Number of cycles in 1 second. The SI system of units uses 1 second for the time interval that we measure a frequency of. You can measure the frequency in other time intervals as well, but for the SI system we use 1 second because the unit is a hertz. So you might have a frequency of 20 hertz would be 20 cycles in 1 second, which is abbreviated Hz. Okay. So those are some definitions there. They're useful terms to be able to use and know how to apply and be able to measure. But in order to think about simple harmonic motion, what we want to do is we want to talk a little bit more about what makes it simple harmonic motion, and that is that restoring force. So I have just a simple drawing here. So what makes it a simple harmonic oscillator and what makes it simple harmonic motion? Well, so here is my equilibrium marked, and I have some positions going on either side. And we're just going to pretend I have an object that is going back and forth like this. Okay, well, my restoring force, so it said it has to have a restoring force, and that restoring force has to be in the opposite direction and proportional to displacement. So if my object goes this way, my restoring force has to be pushing it back like that. And the further it goes, the harder the force has to be pushing. And it has to be proportional to. And if I go the other way, it has to be pushing in the opposite direction. It's still proportional too. So these should be roughly the same size. They should be exactly the same size. You just pretend those are exactly the same size. And then if I come over here, it should be exactly the same size. Can you tell? Look at how exactly the same size those are. You can totally tell. I know you can. Okay. So if this is my force, whatever is causing this force is something else we'll talk about. But this is my restoring force that is causing the object to be pushed back toward that equilibrium. What happens is really cool. Okay. So let's look at these down here. So here's my pendulum. What's the restoring force for my pendulum? Well, when I pull it up, what pulls it back down? Gravity, okay? Now, we'll talk more a little bit about how that works in lesson 2, but just to know that it's gravity right now is enough. What about the mass on the spring? Okay, well, we haven't talked about this one yet, but we'll get to it in lesson 4. There's a spring force, and then this one is even more kind of weird. This one is also a spring force, and there's also that's a botched and sign, and gravity. Okay, so there's 2 things going on in this one, which is going to be an extra complicated problem. So this one is a horizontal spring, mass on a spring, and here we have a vertical mass on a spring, which turns out are really not that bad. It'll be okay. So let's think about what happens and use this kind of simplified problem up here to the energy, okay? So as I pull this thing away, there's a force pushing it back, okay? Now if you think about when this is not the best analogy right now, but when I pull something up off of the ground, gravity really wants it to fall back down, right? So it has potential energy when I pull it away, and gravity pulls it back down. So as I pull it away, it gets potential energy. And when I let go, it speeds up as it moves back toward that kinetic energy. And once it no longer has the potential energy, it's going nice and fast, but it's going too fast and it can't stop, and so it passes it up until that kinetic energy turns back into potential energy again. Can you see my handwriting here? No. And then the same thing happens over again, and so we just cycle back and forth through these. So it has the most kinetic energy in the middle, where the force is actually not trying to stop it. The force is like, oh good, I got you back. Oh crap, you're going too fast. Okay, let me put you back here. Oh crap. It's just a constant back and forth. So that's why it ends up going back and forth like that. So that is what makes a simple harmonic oscillator. Simple harmonic motion is so much fun. So we'll do some more with pendulums and masses on a spring and understand the spring force a little bit better as we move through the unit. Thanks for watching.